continue our discussion of 9.1, and we're going to start off with discussing summation notation. Summation notation is a way to more efficiently write out a sum. This is the Greek letter for sigma, and it signalizes that you should add up all the terms that use this formula, and you start by plugging in 1 for the formula for k, and you go to plugging in n for the formula. K is an indexer, so it goes from k equals 1 to k equals n. And for each of those k values, it will generate different terms that you will then add up. So if we were writing out each sum, we'd first start with k equals 1, plugging it into this formula. So we'd have 1 over 1 plus 1. And since it's a sigma, sigma means add. So it's plus, and then we index to 2. So k equals 2. We have 2 over 2 plus 1, plus, and then we index to 3. And it'll be 3 over 3 plus 1. And since we can't go on forever, we just put an ellipse, another plus sign, and we're going to the nth term. So it is n over n plus 1. And that's how you write out that sum. Likewise, we can expand this summation notation. This one, however, starts with k equals 0. K can start anywhere. 0 is a little odd. 1 is the most typical. But you can really start at any integer value for k. Plugging in k equals 0, we get -1. And then since it's a sum, you're adding. And at k equals 1, you get 0. K equals 2, you get 3. K equals 3, you get 8. If you do 3 squared, which is 9, minus 1, which is 8. And then we're going to skip to the end, plugging in n, because we're going to the nth term. So that's n squared minus 1. So that is how you write out each sum. Now this is going backwards, writing a sum that's already written out in summation notation. So first you have to know the fact that we're going from the first term to the 100th term. And they're being added, so you use sigma notation. So we go from k equals 1, that's the first number in our index, to 100. And the formula here, which generates our terms, is just k cubed. So the first one would be 1 cubed, 2 cubed, 3 cubed, all the way to 100 cubed. Now on the bottom here, we are fortunate that the formula is provided for us right here. And the first term is provided right here. So it looks like I'm going to powers of 2/3. This is 2/3 to the first. This is 2/3 to the 11. So I know I'm going to be indexing from k equals 1 to 11. And I'm going to be taking 2/3 to the kth power. That will get me from k equals 1 to 2 all the way to 11. Next, I note that this power of -1 is to the 12th. That is 1 more than 11. So -1 is to the k plus 1 power. Then I check to make sure my terms work. If I look at my first term at k equals 1, looking at that formula, I'd have -1 to the 1 plus 1 power times 2/3 to the 1. So that's -1 squared times 2/3, and I get 2/3. So my very first term works, which is great. So this is my sigma notation for that sum. So that is how you handle sigma notation. Now, some common sums have formulas associated with them. The first one is the sum of the same number, so that is repeated addition. So if I add a number n times, for example, c n times, that's just a way of saying multiply. So for example, if I take the number 4 and I add it to itself, 1, 2, 3, 4, 5, 6 times, that's the same thing as saying 4 times 6. That's something we learned in elementary school. This is just formalizing that into sigma notation. So that is an old concept written in a new way. This next formula is the sum of consecutive integers. Notice we start with 1 and we go to the nth consecutive integer. And the way we do that is we do n times n plus 1 over 2. So if we're adding up the first 10 consecutive integers, 1 through 10, we plug in 10 for 9. This is the sum of squares. So if you add 1 squared, 2 squared, 3 squared, all the way to n squared, you have this cubic formula. And lastly, we have another formula for the sum of cubes. In a test situation, the bottom two formulas would be provided the bottom two formulas would be provided for you. The top two you would have to know. Now let's see how we would apply these formulas. So let's find the sum of a sequence. So the first thing I can see is that I want to find the sum of all numbers for k equaling 1 through 6. So just to get at what they're actually asking me, for k equals 1, that's 4. K equals 2, that's 8. K equals 3, 12. K equals 4. K equals 5. K equals 6. So this is what they're asking me to do, add up all those numbers. Now I could just do that and get an answer. However, if the top number were 1,000, adding those up would not be a very efficient method. So I'm going to use one of the formulas that was given to us on the previous slide. And the way I'm going to use it is first I'm going to take out a 4 of the sigma notation. Now, when I take out that 4, I will notice that this is the second formula on the prior slide. This is the formula n times n plus 1 over 2. So I can fill in 6 for n because I'm adding up the first 6 consecutive integers. So this is 4 times 6 times 6 plus 1 over 2. So it's 4 times 6 times 7 divided by 2, which is 84. And that is the same as adding all of these up to accomplish the same goal. But again, if you have a whole longer list of numbers to add up, using the formulas is more efficient. Now in part B, we have a little more complicated of a polynomial that generates our formula here. So we have 4k squared plus k minus 1, and you're adding up k's from 1 to 20. So to get the first term, you fill in 1. Second term, 2, all the way to 20. So that could take a little while to generate all the terms and then add them all up. Instead, we're going to utilize the formulas. But I'm going to split these up because I don't have one formula that has all these in it. So I'm going to split it up first into, bring the 4 out, k squared from k equals 1 to 20. We know we can bring the 4 out from the prior example. Next, I'm going to add it to k, and then I'm going to subtract it from the 1. So this is applying the sigma to each term separately instead of applying it all together, which is allowed. It's one of the properties of sigma. So when you look at the formulae on the previous slide, we know that the k squared formula is n times n plus 1 times 2n plus 1 all over 6. So n is 20, n plus 1 is 21, 2n plus 1 is 41, all over 6. And that is the formula for the sum of consecutive squares. And this is our 4. Next, I'm going to look up the formula for consecutive integers. And I'm adding consecutive integers 1 through 20. So again, that's n times n plus 1 over 2. So n is 20. N plus 1 is 21 over 2. Lastly, I am subtracting, adding 1 to itself 20 times. Adding 1 to itself 20 times. That's just subtracting 20. And when I do that, I get 11,670. And that's a lot quicker than adding all of those 20 terms up that you have to generate by plugging it into that polynomial. So that is 11,670. Lastly, one of your homework questions will ask you something like this. Find the sum of k squared from, let's say, k equals 7 to 20. Well, that's a little challenging because all of our formulas are from k equals 1 to 20. So what you have to think about is the fact that the formulas go from 1 to 20. So what I'm going to do is calculate what it would be from 1 to 20. But then what I can do is take away what it would be from 1 to 6. Because this is 7 squared, plus 8 squared, plus 9 squared, plus all the way to 20 squared. The red one generates 1 squared, 2 squared, 3 squared, 4 squared, all the way to 20 squared. And then this green one will take away 1 squared to 6 squared. Then accomplishing my goal of adding up just 7 squared through 20 squared. So your homework is going to be simply to finish up this assignment doing every other odd 15 through 79.